Hello. Hello, everybody who's logged in. And I know it's going to take a couple of minutes to log in. So let me just talk about what we're doing here today. This is Meela Mitra on behalf of Space India. And I have with me Dr. Madhulika Guhathakurta from NASA, joining us from the US. And we also have here with us Achal, uh, Achal Tandon, who is also our educator in charge. So on behalf of Space, she will be asking all the questions that our students who are joining in today will have for you. So, as a set of, for celebrating Global Astronomy Month, we've been doing a series of lectures with prominent scientists in the US who kindly join us to talk to our students. So, this is also in that series. So, we are going to go ahead and get started. Today, we have with us Dr. Madhulika, who I will call Lika, Guhathakurta. She is the program scientist in the Heliophysics Science Division at NASA headquarters. Dr. Guhathakurta has been a Heliophysics Science Program Manager at NASA headquarters for 18 years. In that role, she has led the Living with a Star program for the past 15 years, whose goal is to understand solar variability and its diverse effects on Earth, human technology, and astronauts in space. She is the program scientist for Stereo, SDO, IRIS, and other missions. Dr. Guhathakurta has worked as an educator, scientist, mission designer, directed and managed science programs, and has built instruments for spacecraft. She has been a co-investigator on 5 Spartan 201 missions aboard space shuttles to study the solar corona in white light and UV radiation. She has been a long standing Eclipse enthusiast and NASA science lead for the upcoming Eclipse. I'm so happy to welcome you here today, Dr. Guhathakurta or Lika. And I've known Lika personally for many years, and I'm very happy personally that she's joining us here today to talk to our students. So welcome, Lika.
Hi.
And I'm also going to introduce Anchal. She's our educator in charge. And welcome here, Anchal, today.
Yeah, thank you,
So,
Mala ma'am, and welcome, Madhulika ma'am. We are really excited to have you with us because students, we have been learning about this. We have been trying to learn all these things for like since the time we have joined the organization, and all the students are so excited to meet to see you online. So I hope that they're gonna learn a lot of things and they're gonna ask you a lot of questions after the interaction.
That'll be a
yes.
pleasure. It's almost 12-hour difference. So while you guys are all waking up, maybe I'll be a little sleepy.
Yeah.
Yeah. So get
Right.
your coffee
Keep me
so we
going.
can, yeah, because the students will have a lot of questions. Anchal is right. So we're going to go ahead and get started. So, let's, Madhulika, we're very excited because we have you on board today, and the solar eclipse is coming up in August in the US after a long time. So everybody's all gearing up for that, and I know you're one of the prominent scientists working on eclipse observations. So I request you to go ahead and tell us a little bit about yourself, and then get started and talk to us about your presentation. And after that, Achal will bring forth the questions that our students will be posting that would be based on what they hear from you. So, Dika, go ahead and tell us about yourself and the presentation.
Okay, so should I share my screen at this point?
Yeah, you can go ahead and share your screen,
Okay.
and it should show.
Let me get started.
Uh, Not yet. We can still see you.
Oh,
So
I guess the share didn't work in that case. Oh, let me do share.
yeah.
Ah. How about now?
Uh, we can't see it yet now. So you're trying to do a screen share on the,
Yeah,
yeah, and we still see you.
I am doing the screen share. Chrome.
So
Use
do
what?
you also, while we talked, do you also want to mail me the presentation so I can also bring it up if needed?
This is too big because it has embedded
Okay,
movie.
now, yeah, we see it now. We see it now. Okay, so all you have to do is bring your presentation slide to the front. That's right. We see it
Okay,
now. So you can do the full screen.
okay, all right. It's, I think it's
And again,
definitely
folks, we have,
low.
yeah. Yeah, that's fine. That shouldn't be
You
a
see
problem.
now?
Yeah, we see it now.
Perfect.
Perfect.
Okay. Well, so I have quite a few slides, and maybe you can tell me at some point to stop so that students can ask questions. What I wanted to do is kind of give you a little background on heliophysics and space weather, which is kind of a more common term that is used to refer to heliophysics, even though space weather is just an aspect of heliophysics, and then really discuss the 21st total solar eclipse that is about to take place in the continent of USA. But just to put the total solar eclipse in context of heliophysics and space weather. So I'm going to go through with the heliophysics part and talk a little bit about the sun in the beginning. You already heard about who I am and what I have done. I've been a heliophysics scientist for a very long time, trained as an astrophysicist from University of Delhi, long time ago, and then essentially concentrated my effort on really looking at just only at one star, and that is the sun. And that's how I entered into my present role at NASA headquarters in the heliophysics division. Heliophysics is a new term, a new discipline, which kind of looks at the variability of the sun, but just not that, it's the variability and its impact on our planet, on the interplanetary medium, and all other stars. So in this particular slide that you're looking at, it just gives you a beautiful picture of total solar eclipse from, I believe, 2008, where the visible bright disk of the sun that we are used to seeing every day is blocked out because the moon has now come between the sun and earth, and it really blocks that sunlight. And when we do that, out emerges this beautiful halo around the sun called the corona, which is the outermost atmosphere of the sun. And what you see are these thin, wispy rays around the sun. And the reason that this structure is so sculpted, there are so many variations, thin rays, is simply because this is sculptured by the magnetic field of the sun. And magnetic field is a word that I will come back to over and over again. So we call this the 100-year eclipse. The last time such an eclipse actually took place in USA was almost 100 years ago. It's an eclipse that sort of crossing over the entire stretch of USA from West Coast to East Coast. People will be able to see, at least within a 100-mile band, total solar eclipse, but pretty much the entire continent will be viewing various partial phases of the eclipse. Now, of course, what's NASA's role in this effort? This is a celestial event. We don't control it. Nature controls it. But NASA is trying to play a role in terms of informing the general public, students, regarding the safety precautions that needs to be taken while you are looking at the sun. You're not supposed to look at the sun directly without protection. unless you are watching the total solar eclipse, kind of the picture that I'm showing you right now. We are interested in promoting science related to the eclipse. And what's fascinating is eclipse kind of covers not just solar science, but earth science, planetary science, astrophysics. There have been a lot of discoveries in the past that have been made, from eclipse observations of the past. There is, of course, a great emphasis on education, on the engagement of citizens in performing citizen science, simply because the path of totality is so long through the continent of USA. And of course, public engagement in that process. And the lower plot simply gives you a picture of some of the upcoming eclipses that will go through 2052. Fascinating enough, there'll be another eclipse that will cross through USA in 2024, just 7 years later. Eclipse, it's kind of a rarity that you get to see an eclipse from the same area more than once in your lifetime. Sorry about that. I hope you can hear me better now. And so that variability that you saw essentially has its impact on the solar system. So sun puts out electromagnetic radiation, which is the entire spectrum of black body radiation curve, plus flare, which are these intense activity that takes place on the sun and produces enormous amount of energy. But it also puts out mass in the form of continuous loss of particles called solar wind, coronal mass ejections, which are these huge solar storms that take place, also carrying billion tons of matter in the form of electrons, protons, and other ions. And of course, solar energetic particles, which does a lot of ionization of the environment. So if we start with the way the solar through solar dynamo, we can take sort of two different branches. So the magnetic flux emergence, the dynamo creates magnetic flux, which then produces sunspots, these dark regions on the sun, which creates active regions, which then become sort of seeds or regions where these storms manifest. And then on the other side, you have, basic electromagnetic radiation, radio waves, visible light, X-rays, ultraviolet rays, etc. The sunspots and the active regions essentially produces flares, solar energetic particles, produces coronal mass ejections, which then propagates through the interplanetary medium, creating shocks and impinging on our magnetosphere, on our planet. And I'll show you some visuals of that, which then causes internal instability inside our magnetosphere, causing current and voltage fluctuation, which can, sometimes give rise to beautiful auroras. Sometimes they can actually affect our power grids, cause voltage malfunction. There are all kinds of deleterious effects that can happen and do happen from this coronal mass ejection. And as you can see on this chart, on the left-hand axis, this interaction goes all the way from solar convection zone out into the heliosphere. So it's not just our planet. All planets and everything in the solar system are affected by these events. So the mass chain, as I talked about, are coronal mass ejections, solar wind, and solar energetic particles. And space weather, essentially, it's related often to coronal mass ejections and its ability to cause geomagnetic storms, which is causing storms in our environment, that is in the terrestrial environment, in Earth's environment. And climate is also affected by solar variability, and that particular chain is essentially the electromagnetic radiation with a little bit of contribution from the particles. And this gets a little complicated, but if you keep this in mind, so there are matter that is being ejected, and then there is just basic radiation. So where is our place in the Milky Way? Sun is located at a distance of about 26,000 light years from the galactic center and slightly displaced from the galactic plane. As you can see in that picture, it's that thin arm of the galactic spiral. And the arrows point to where we are. This is a picture that was taken, imaged by the Hubble Space Telescope. And these arrows are continuously kind of pointing you to where we are in the Milky Way galaxy, where the sun is. And then, the sun essentially has the solar system with its 8 planets. Of course, this is an older picture I can see, as Pluto has been demoted to a dwarf planet. Nevertheless, this is our solar system. So that kind of gives you a picture of how minuscule we are, sort of makes you humble when you think about our place in the universe, or in this case, just the Milky Way. And I haven't taken the Milky Way and put it in the context of the universe here. So I'm sorry, this is also, how do I, this actually stopped, good. So this is actually an important chart that I wanted to talk about a little bit more, simply because, this kind of asking the question, why do we do science, or why do we study the sun, for example? in this case, I think what we are trying to say is that all research that we do can be plotted on two axes, okay? Curiosity versus utility. And the results that emerges when you plot this on such a chart are three distinct classes of research. Pure basic research, exemplified by the work of Bohr, Niels Bohr, you know, who was the early 20th century atomic physicist. Pure applied research, exemplified by the work of Thomas Edison, inventor. And then there in red is what is called the user inspired basic research, called the Pasteur quadrant, where it is half curiosity, half utility. And within the heliophysics context, we have a program, Living with the Star program, which kind of embodied itself in going after science that is relevant to life and society. So it has both curiosity and application as fundamental basis for the science. This is also the area that we call space weather, essentially. And overall, why do we study the sun? We are trying to understand the sun and its interactions with the earth and the solar system. We're trying to do fundamental physics, which is the Bohr quadrant. And then we are trying to understand sort of our nature of our home, our planet in space, which is both in Bohr and Pasteur quadrant, and then build the knowledge to forecast space weather throughout the heliosphere. That is, really characterize the heliosphere and planetary interactions throughout the solar system by understanding the solar variability and individual interaction with each medium, whether it's our planet, whether it's Mars, whether it's Pluto, whether it's the Voyager spacecraft that is actually leaving our solar system and entering into interstellar medium, so getting into the Milky Way domain. But this is the physics we are also trying to learn. Well, space weather clearly begins with the sun. And as Heraclitus said, the sun is new each day, at least it is for me. And if the sun had no magnetic field, as I was saying, it would be as dull as most astronomers think it is. And that was said by a famous astronomer, Leighton. And if you don't
this magnet
Leighton
is really a miniature model of all things. The earth, sun, trees, cells, everything is shaped by magnetic fields.
Had to show that is really cute, kind of in the Twilight Zone format, kind of exemplifying the importance of the magnetic field as I view it. This is a picture that's kind of showing you the blue marble planet. When you look at our planet, it's often we think that think of two words, right? Splendid isolation. It is surrounded by millions of miles of essentially uninterrupted black. But that is not really true. Earth is actually profoundly connected to our star, and the bright blue disk is just the most obvious evidence. What you're seeing in the movie, which is to the right, this cocoon that's kind of quivering in the wind, is essentially our Earth's magnetosphere really responding to the solar wind radiation, pressure, and interaction. These are invisible magnetic field lines, essentially, that are shape almost looks like a cocoon quivering, but this magnetic field, this magnetosphere, Earth's magnetosphere, also acts as a shield for Earth to protect Earth from the harmful radiation of the sun. So you can clearly see the connection between our star, the sun, and our planet. We actually live in the outer atmosphere of our star. The other picture on the lower right-hand corner, what you see is a beautiful movie image taken from space station showing aurora borealis. When you see either a northern or southern light, aurora borealis or aurora australis, what is very clear is that there is a geomagnetic storm taking place in our own environment as a consequence of a solar storm or solar wind interaction. What are some of the global effects of space weather? This is a picture, a movie essentially that gives you kind of many different kinds of technological impacts. And what you're seeing here, a coronal mass ejection, billowing out a ton of material in the form of electrons, protons, traveling very fast and impinging on our magnetosphere. In the process, these plasma particles can interact with sensitive electronics of spacecraft and cause single event upset. It can cause aurora borealis. It can actually create voltage fluctuation on power lines and trip our transformers and create blackout. It can actually cause malfunction of GPS navigation system, cause problems in communication navigation. High altitude airplanes will be exposed to radiation. It's just anything that is electromagnetically sensitive, has an electric on-off switch, including an ATM machine, has the potential to be affected by space weather. And as our societies are getting more and more technologically vested, I think our dependence on understanding and predicting solar storms, that requirement is increasing hugely, because this can impact our societies in very many ways and cause $1 billion of damage. So very quickly, so what is terrestrial space weather? And I use the word terrestrial space weather simply because we have space weather on Mars, and we have space weather on Jupiter or Pluto, any planet you can think of, or even you can imagine, a comet kind of interacting with solar wind, and that would be space weather local to its environment. But for our planet, whenever there is a coronal mass ejection, there is a huge amount of material that is ejected. So flares and coronal mass ejections will give rise to electromagnetic radiation. Typically, your ultraviolet and X-ray radiation travel at the speed of light, and it takes about 8 minutes to get to Earth. And this is the NOAA R scale that causes radio blackouts, that can cause drag on satellite because it ionizes the ionosphere and increases the momentum of the particles there. Then, of course, the coronal mass ejections are the ones that carry matter, charged particles essentially, which are slightly heavier and take a little longer to get to Earth, of the order of 10 to 30 minutes. These radiation affect astronaut health, aviation, and satellite malfunction. And then finally, the big blob of magnetized plasma essentially arrives, depending on the speed with which the coronal mass ejection was ejected. The storm happened anywhere between 18 to 96 hours. If it is 18 hours, we know that if it is Earth directed, there are potentially some big consequences that can take place. So this is, in a nutshell, what happens in the world of space weather. So this is as our understanding of the Sun-Earth connection and space weather is increasing, our need to kind of observe the sun continuously and from different vantage points has also increased tremendously, just to be able to accurately predict, when a storm will arrive at Earth, because that knowledge really helps towards mitigation of some of the harmful effects of space weather. And so NASA and other space agencies have many different spacecraft that they have launched. You know, SOHO is almost 20 years old. We have Solar Dynamics Observatory launched in 2010. We have 2 stereo spacecraft that moved away from the Sun-Earth line, giving us a full view of the sun from different vantage points. So we have many different spacecraft really looking at the sun in different wavelengths, different angular and spatial resolution to understand the solar storms, to understand the emergence of magnetic fields so that we can better predict the conditions. This is your solar cycle. So sun sort of has a heartbeat, which is every 11 years. It waxes and wanes. So the solar magnetic field increases and the sunspot number increases as a consequence. And then the frequency of the solar storms also increases during the peak of the solar cycle. Not the strength necessarily of the storm, but the frequency. Definitely. And you can see, obviously, from this plot, the amplitude varies quite a bit. And in the way things are shaping up to be, it seems like in the last couple of solar cycles, the solar magnetic field is weakening. And so the sunspot cycle is actually weakening. And that has its own consequences. One thing to keep in mind when you are looking at a solar cycle variability plot, which is plotted as a solar maximum and minimum, and often we have a tendency to think that all the bad things happen during a solar maximum where solar magnetic field is the highest, sunspots number are the highest. Well, that's not necessarily the case. For example, you know, I kind of tried to change the orientation of the plot and plotted it sideways so that we are not concentrating on maximum or minimum, but we are looking at the solar cycle as 2 ends, 2 extreme points, okay? Low sunspot number, high sunspot number. Like in climate, we have solar La Nina, solar El Nino. If you look at the kind of space weather effects that happen, you can see that there are events that happen during solar minimum and solar maximum. So space weather really never disappears. Aspects of space weather essentially swings between extreme effects of the solar cycles. For example, during solar minimum, you know, we have accumulation of space junk in the ionosphere. There is a sharp contraction of the heliosphere. Total solar irradiance changes slightly, and that has an impact on the climate change or the global temperature, for example. So these are facts to keep in mind, not to get carried away by solar maximum and think that nothing can happen during solar minimum. This I won't go into detail, but quickly show you how
this point, I just want to tell you that we would give you another few minutes for the presentation because we have many students waiting to ask questions.
So let me go, then move on to the eclipse stuff very quickly, okay?
Yeah.
These are essentially all showing the global impact of space weather. We have also books available now, students being trained in the field. So you students someday might be able to participate in this. I take that you are in high school. So let's quickly talk about the 24th total solar eclipse. Eclipses happen when the moon, total solar eclipse of the sun happens when the moon comes in between the sun and earth, and essentially the point of the umbral shadow, the tiny dark dot, is where the entire visible disk of the sun is covered, and we see the corona. And that's the picture of the corona. If you are in the path of totality, this is what you would see, these white billowy clouds. Now, we do not get a total solar eclipse during every new moon simply because of the orientation, the plane of the moon, Earth, and the sun. And also, we always don't get a total solar eclipse. Sometimes we get an annular eclipse, depending on the angular size of the moon as it appears, depending on the distance of the moon from our planet during its perigee and apogee. This is a movie that shows you, it's going to give you a picture of this shadow essentially as it will be coming from the Pacific Ocean all the way through the coast of Oregon and then crisscross through the entire country and then emerge out in South Carolina, in Charleston. This is seems like the movie is pretty slow. You get a picture that pink band there is the path of totality, and the outer bands there are where you're going to see partial eclipse. And I'm going to show you another movie which will give you a picture of the partial phases of the eclipse that will be experienced by pretty much most of the country. And these partial phases are what you are seeing as the shadow, as the moon sort of comes in front of the sun. And since I'm running out of time, I'm not going to run this fully. These are pictures that are taken from spacecraft and instruments on board spacecraft. And these are pictures of the shadow of the moon being taken from spacecraft. This was done during 2016 eclipse. It's really cool. And we are going to do that, of course, for almost 90 minutes of totality during the 2017 eclipse. This is yet another movie. These are, it takes time to show the movie. What this movie is trying to show, it's giving you a map of the United States, but it also shows how we are cutting off the brightness of the sun. And you can see as you cut off the brightness, you are actually bringing in less radiation on the planet. And so there'll be lots of interesting meteorological effects and students being engaged in making measurements of temperature, wind velocity, all kinds of effects, and animal behavior as this darkening continues to happen. This is a more detailed picture of the shadow band that has been, I'm not sure if this will play. Unfortunately, I had to change my laptop, so this laptop might not play the movie. Let me go on to the next slide, which shows many of the things that NASA is doing. We are going to be observing the solar corona. We are going to be observing the moon, under the lunar shadow. We are going to have high altitude balloons. We are going to have measurement from aircraft. And then on the ground, we have a host of different kinds of experiments that are being conducted, both to look at the sun as well as understand the effect on weather on Earth, on our ionospheres. So there's going to be a tremendous amount of detailed data that will be collected during this eclipse. These are some of the experiments that we are going to conduct. As I said, seeing the solar corona and observing solar eclipse, observing the eclipse from the ground globe, doing essentially temperature measurements. We are going to observe the Earth during the eclipse. Some of the images I showed, perhaps through space station, we will know whether the space station will be in position to actually image the corona. And then we have our Earth science satellites, Terra, Aqua, Landsat, that will be doing meteorological observations. We'll be studying the moon during the eclipse. Wanted to point out, not during this eclipse, but eclipses actually have led to sort of the finding of exoplanets. You know, when you have a planet go in front of a stellar object, there typically will be a dip in the brightness variation of that star. And that's how we actually discovered exoplanets. So eclipses have led to all kinds, including, you know, verifying Einstein's general theory of relativity. So it has, through you know, generations, it has led to many discoveries, not just of solar physics. This is the kind of study we intend to do. This is a picture taken from 2008 with a white light coronagraph, ground-based. Eclipses allow us to observe the corona very close to the surface of the sun, and that's what makes it unique. You know, with NASA spacecraft, we artificially create eclipses every day, every minute, but the eclipses that we create with our telescopes do not get that close to the surface of the sun in white light. We can do that in soft X-ray, but not in white light. And that has unique sort of capability to for our models and for our understanding of the three-dimensional you know, density configuration of the corona and its magnetic field geometry. So I'm coming pretty much, I have one more slide. I think I'd like to kind of say that as a singular event of some national scale, and with a global audience in this case, you know, there'll be lots of people traveling to US. This event will rival the moon landing of 1969 as a landmark event for a new generation. It has the potential to really contribute in economic, political, scientific, cultural, intellectual, and spiritual domain. It's going to change a generation almost, I feel. If you have seen a total solar eclipse, and I have been to 9, and I have seen 6, it has a transformative effect on you. There is no other heavenly phenomenon that we can watch in this form with our naked eyes. It is quite a spectacle. And finally, I kind of want to end with this slide, is that, of course, nature allows us to see the solar corona, you know, and very close to the surface of the sun. But ingenuity of human being also allows us to actually get close to the star and start taking measurements of that plasma environment with real spacecraft in order to really understand, you know, the number of particles in that environment, the actual strength of the magnetic field, because everything we measure from Earth is a remote sensing measurement, and so it has a line of sight integration effect. So we cannot detangle that. We will be sending a mission to the sun, to within 10 solar radii of the sun. You can see the path that it takes through that elliptical shape that there is. And this mission will be launched next year, around end of July, August timeframe, to get to within 10 solar radii of the sun, to really sort of address some of the fundamental questions we have in solar physics, which is the surface of the sun that we see is, you know, of the order of 5,000, 6,000 degrees Celsius, whereas the corona, which is this material that you're seeing blowing out, the outer atmosphere, is of the order of 1 to 2 million degrees. So what makes the corona so hot? What provides the energy and momentum to the electrons and protons for solar wind to continuously blow out, both as slow solar wind and fast solar wind? And so this mission will be going very close to essentially give us observations that will help us answer some of these questions. And with that, I will take your questions.
Certainly.
So,
Thank you,
thank you,
Madhulika.
Madhulika.
Yeah. And Achal, go ahead.
Go ahead.
All right, Nala. So, thank you so much, ma'am, for this nice interaction. And, ma'am, now I have got a lot of questions from the students. The first question is from St. Thomas School, and it is from Ananya. Am I audible, ma'am?
Yes, you are.
Hello?
Yes.
Yeah. All right, ma'am. So, the first question from Ananya's side is that what is the difference between sunspots and coronal holes?
So sunspots are regions of very intense solar magnetic field. And they appear dark, but they are actually not dark. They appear dark because the magnetic field is so strong that it inhibits heat conduction. So compared to the surrounding region, it appears dark. So that's your sunspot. Coronal, and so they are magnetic fields that are closed. Coronal holes, on the other hand, are open magnetic field region, and the magnetic field there is weaker, and the magnetic field is open, and solar wind essentially streams out only from open magnetic field region. Typically, coronal holes are associated with the poles of the sun, but you can have coronal holes anywhere on the sun.
All right, ma'am. Can I ask the other question?
Yes.
Yeah, all right, ma'am. So, ma'am, this question is from Akshay, class 9th, Rukmani Devi Public School. So, he's asking that
Just a
according to
second,
NASA,
Madhulika. Can you get yourself back on the screen?
Oh, let's see.
Okay, Achal, yeah, go ahead.
Ah, you
yeah.
see?
So, yeah.
Okay.
So, ma'am, the question is that according to NASA, the sound of sun is Om. How did they recorded the sound in the space as sound doesn't travel in space?
So it is essentially what we are doing is we are making measurements, and then just for example, when you look at sun in red or blue color, we know that the sun doesn't have that color either, right? So we give it
Yeah.
an artificial color. So we are actually able to measure sound waves through Doppler shift measurement on the sun. And then you can give it an audio value, just like we give temperature scale to color, even though, X-rays don't have a color because we can't see X-rays, for example. But we give it, we have intensity map, and we can actually provide a color table. In the case of actually measuring sound waves in technology, we actually take the measurements to Dopplerograms, and then you can render it into sound.
Thank you, ma'am. Now, ma'am, the next question is from Daksh Arora, KR Mangalam School, Vikaspuri. He's asking that how can sun produce electromagnetic radiations?
How does anything produce electromagnetic radiation? That's a very good question. It's a very fundamental question. Whenever you have electric and magnetic field, so this is, you have waves and you have particles, and these interaction will produce radiation. And electromagnetic radiation essentially covers the entire spectrum, right? Going from your very high energy radiation like gamma rays to very low energy radiation like infrared rays. So sun has a dynamo, and the sun rotates. So the dynamo produces magnetic field and it rotates, which produces current. And the interaction essentially of the magnetic field, the current will produce electromagnetic radiation. At this level, will be harder for me to explain the source of electromagnetic radiation. It is a very fundamental aspect of physics, kind of like, atomic physics, like particles, what holds essentially your electrons in orbit, or what gives them the spin state. So it gets a little bit tenuous. Mila, do you have a simpler way of explaining?
All right, ma'am. Thank you. Ma'am, now the next question is from Utkarsh Nath from Army Public School, Noida. That how do sunspots have intense magnetic activity?
Ah, so so these are so when when I say there is a dynamo, so sun is rotating. Think of it like boiling a pot of water, and so when the water boils, you have these bubbles that come up, right, and dissipates energy on the top, and then it goes back down. So these constant turning of the sun produces magnetic field which gets twisted and comes out from certain areas because of their orientation, because of the speed, it could be because of longitude, that will create these clusters essentially. And these clusters emerge as strong areas of magnetic field, but lots of work is being done in India, kind of showing how these magnetic field emerges from different areas. And so and that's kind of the source. The dynamo is the source, the rotation of the sun is the source, the variability of the composition in the convection belt is a source. They all kind of convolve together and produce clustering of magnetic field. And you will see these also vary over 11 years, as well as the migration of sunspots from high latitude to low latitude as a function of solar structure. So it seems to be periodic, and we are getting a better handle on it.
So, Madhulika, do you have a few more minutes so we can take a couple more questions?
Yeah, ma'am, because there are a lot of questions coming up from the students.
I am here. If you guys have time, I can say.
Yeah,
Okay,
all
so
right.
Anchal, we'll go ahead for another 5 minutes or so.
All right. Okay, ma'am. So this question has come from Onkar from Delhi Public School, Greater Faridabad. So the question is that what is R scale, G scale, and S scale, and what is the temperature of the sun on the sun?
Okay, so the RG and A scales are three different scales that NOAA, Space Weather Prediction Center, have come up with, essentially trying to mimic the way we predict, terrestrial weather. So R scale is the radio blackout. When you have a radio blackout, when there is a solar flare and storm, X-rays and ultraviolet rays, and that causes ionization of our ionosphere. X-scale is essentially the creation of energetic particles, um, and that could be essentially coming directly from a flare, or it could be shock waves produced from a coronal mass ejection in the interplanetary medium. And the solar energetic particles then causes radiation conditions, for astronauts, for high altitude aviation. It can also cause single event upsets on sensitive electronics of spacecraft. And G scale is the scale that is probably of most importance to us on Earth, because G scale comes from coronal mass ejection, and this is this billion tons of matter kind of pounding on our magnetosphere, which essentially creates current and voltage fluctuation on power grid, and power grids become sensitive to this voltage fluctuation, and transformers can actually melt down, and that has actually happened back in 1989. And when transformers melt down or malfunction, then what you have is disruption of power. And when you lose power, electricity, then pretty much most of your technological systems stop working. So that can be pretty devastating if you are not prepared for it.
Yeah, ma'am. So the next question is from BBPA, Bal Bharati Public School, Pitambura. The question is that what is the state of matter of corona?
Say that again.
Ma'am, it's what is the state of matter of corona?
So I'm not quite sure what that means. So corona, if you are trying to kind of understand whether it is solid, liquid, or gas, it's none of that. Corona is in a state that's called a plasma state. It's the fourth state of matter, and this is where particles are not neutral. Particles are charged. So an atom has most of its electrons, separated from it. So you have a population of electrons, you can have population of protons, and you have highly ionized atoms. So it is in a state of what we call a plasma state, magnetically charged state. I can't hear you.
Yeah, sorry, ma'am. All right. Ma'am, the question is from Lakshay Gupta, 9th A. He's from Presidium School, Gurgaon. Now, he's asking that will the size of CME increase when the size of the sun increases?
There is no evidence for that. When the size of the sun increases, when the sun goes into the red giant phase, um, there is no reason to believe that the size of the CME will increase. I don't think anyone has done any calculation, what the magnetic field conditions will be, what the state of the dynamo will be when the sun becomes a red giant. That's the question when the student is asking when the size of the sun increases, because that's when the size of the sun will increase.
All right, ma'am. Next question is from DPS Sushant Lok, Delhi Public Schools Sushant Lok. The students are asking that currently sun is in its middle age. Will its electromagnetic radiation will be able to control the planets around it? And if not so, will the planets crash in the solar system?
So the electromagnetic radiation does not control the planets. It's basic sort of celestial mechanics, Kepler's law, gravity that controls the planets around the sun, not electromagnetic radiation. Electromagnetic radiation really interacts with the environment. So for us, it interacts with our magnetosphere, ionosphere, for example, right? For other planets, depending on whether they have a magnetosphere, ionosphere, whatever the condition might be, that will be the nature of interaction. So it does not, electromagnetic radiation does not keep the planets in place in their position.
Ma'am, next question is from KR Mangalam School, which is in Greater Kailash too. So the question is from Akshay, that can solar flare result Earth catastrophic in future?
Um, there is always a possibility in the sense that, a big solar flare. We had a big event in 1859. Now we have had, strong solar flares in the past. The reason it can have a catastrophic effect on Earth is through technology, essentially, not any other way. It's because we are technologically dependent, and if our technology is taken away from us, just like I was saying, if we lose power, for example, then imagine how many different kinds of, you know, sort of daily objects we use to carry on livelihood, from hospitals to finance to elevators in building, everything is going to go away. But that's our dependence on technology. If we were simply, living by the ocean, raising rice and, fishing in the sea, then a solar flare, even a strong solar flare on the sun wouldn't do us any harm because we are no longer dependent on technology. So that's kind of the dependence and the catastrophe that solar storms can create. It's an indirect way of affecting us, but it can be pretty profound.
You. Thank you, ma'am. Now, ma'am, the next question has come from CB, sir. He's the president of the Space Foundation. So he is asking that he would like to know more about the KP index.
So KP index it's a very complex index, and even I don't understand it very well. And it is actually created by taking measurements from ground-based magnetometers, and then and its variation, essentially. It's kind of created as a function of latitude and then correlated with solar wind observations. So KP, for example, NOAA will often kind of give you a value of KP index to indicate, how strong geomagnetic storm is. It's always, there isn't always 100% correlation, like a strong KP index will lead to a strong geomagnetic storm. But, if there is a strong KP index that is measured, that is as often used as a signature that something strong might happen. And in this case, again, when we talk about a strong geomagnetic storm, we are really kind of looking at the vulnerability of our power grid. And I think KP index is a measure of the magnetic field on Earth. Because all of these get foretold through the interaction of the solar magnetic field linking up with Earth's magnetosphere and ionosphere.
So, Achal, we'll take the last couple of questions.
Yeah. All right, Mela. So, ma'am, the next question is from Gautam Reddy from Balbharti Public School. He's asking that why does the sun's polarity flip every solar cycle and how will it affect the CMEs?
So this is also again a complicated question and with ongoing research. So even though we say solar cycle is 11 years, in reality it is actually sort of 22 years because the cycle, so the like an ordinary magnet has a north and a south pole, ordinary bar magnet. In that simplistic sense, sun also has a north and a south pole. And so the polarity of the northern and southern hemisphere are different. And it's every 22 years is when the sun comes back to the same polarity in the same hemisphere. And the way that happens is, again, through migration of magnetic field through the dynamo process and diffusion, that takes place essentially, where your sunspots will essentially go poleward, get merged with the polarity of that particular hemisphere, then it returns back to the other hemisphere. So it's a complicated process, takes about 22 years, but this is something that is relatively well understood, and people are actually able to model the phenomenon.
Yeah. All right, ma'am. Another question has come from Venkatesh, who is from ASN School. He wants to know that radiation emissions can affect our atmosphere adversely, but can they do any more damage to us?
So I don't know what more damage mean. Um, can you be more specific? I mean, typically, what does radiation do? Radiation damage is biological damage. It can change DNA
The skin
structure.
or the
The
eye.
DNA structure can have, impact for future generation if the people with DNA damage procreate. So it can get acutely radiation sick. That's one. You can over time build up a lot of radiation, so that will again make you prone to cancers and other kinds of diseases. And then, of course, it causes DNA damage.
So, Achal, I'll take the last question. Madhulika, where will you be during the 2017 eclipse? And which you mentioned so many activities and experiments that NASA will be doing, but which one will you be involved with? And yeah, let's just hear about that too, and then end this interaction.
So that's a very good question. I have three possibilities right now, and do not know exactly where I might be. So if I could, I would be on an airplane, simply to guarantee seeing the eclipse, So I know there'll be no cloud cover, right? If I'm on an airplane. And NASA will actually have a couple of planes, one that will conduct experiment, one that will actually take images of the corona for public engagement. If that doesn't happen, then I'm going to be in the state of Oregon, either at Salem, where we have solar physics division meeting, big meeting taking place with, a lot of the solar astronomers there, or in the city of Madras, where we have actually an experiment from NASA Goddard Space Flight Center. In fact, we actually took this experiment to Indonesia last year, but we were not successful in our endeavor because it rained during the total solar eclipse. That's the reason I want to be on an airplane. I can't hear you.
Yeah, sorry. Yeah, that brings us to the end of this conversation. And, it was so great talking to you. And we're going to hopefully follow you and see what happens during the eclipse, since we are not going to be able to see it. We are going to try to get live webcasts or tap scientists such as you to involve us in some way. And, in 2010, Space also organized an eclipse flight, and some of our students and teams were able to see the eclipse from a flight, like you're saying. And we hope to share your experiences as we get to the eclipse. And I just want to share that today we had 280 viewers, and we had at least 8 to 10 live classrooms that were logged in. Thank God you didn't know that. but you had full classrooms that were logged in and watching you. So this was a great experience, and thanks for being with us here today. Do you want to just give us a couple of last words to inspire us?
This was a pleasure. Sorry for the initial technical difficulties that took some time, but I think if you get the hang of the hangout, then it's not a difficult thing to do, and this is perhaps a good way to communicate with the students. And I would love to participate in future again and talk in greater detail. I didn't get a chance to really go in depth into solar eclipse, but there is just a lot going on in terms of what we are planning with students, citizen scientists that your students would be interested in. And go to the NASA website, 2017eclipse.nasa.gov. So you can find lots of thought experiments and other stuff that's going on.
Achal, do you have anything you would like to add?
Ma'am, actually, we have got a lot of information today. We had a lot of questions. I myself had a lot of things to ask, but then we're gonna ask you offline. Then we're gonna find you somewhere and catch you to ask many questions about solar astronomy now. So it was a very nice experience, ma'am, and I think that students have also enjoyed it. So thank you so much on behalf of all the students and all the educators who are there with them for giving us your time, and sorry for disturbing your sleep.
Oh, don't worry. Thank you.
Thank you, Madhulika, again. On behalf of Space, let me thank everybody who's joined us here today. So many students, members of the public, Achal, and most of all you, Madhulika, for sharing your experiences with our students. And we are going to take you up on what you just said and invite you for more interactions. So thank you.
Students had a lot of good questions. They are clearly paying attention. Thank
Okay.
you.
Thank you. And
Thank you, ma'am.
bye, everybody, and good night, Madhulika.
Bye.
Bye, ma'am. Thank you so much.